Welcome back to the Explainer. Today, we're zeroing in on a hazard that is completely invisible, makes absolutely no sound, and is incredibly easy to overlook until it is, well, entirely too late. When we think of industrial explosions, especially out on an offshore rig or a heavy chemical facility, we instantly picture an electric spark, right? Or maybe a severed cable, or a sudden arc from a switch. But what about the path to ignition that literally everyone forgets? We're talking about the silent danger of heat. So it's time to shatter a really dangerous misconception right out of the gate. You absolutely do not need a spark to start a catastrophic explosion. Seriously, a hot motor housing sitting quietly in a gas cloud is more than enough to trigger the whole shebang if its surface gets too hot. No fault, no arc, just a hot surface. This is the invisible ignition path everyone forgets about, and understanding it is absolutely crucial for anyone involved in hazardous area safety. Okay, let's dive into this. Every flammable gas out there has what's known as an auto-ignition temperature, or AIT. Think of this as the exact thermal threshold where a gas mixture will just spontaneously self-ignite with no external flame or spark whatsoever. Crazy, right? On the flip side of that, every single piece of electrical equipment has a maximum surface temperature that it will reach under its absolute worst-case operating conditions. So the golden rule of auto-ignition is actually pretty simple. The equipment's maximum surface temperature under those worst-case conditions must never, ever cross the gas's auto-ignition line. To keep all this safe and standardized across the board, the industry categorizes this data into temperature classes, or T classes, ranging from T1 down to T6. Let's walk through this data from the IEC 60079-14 standard. A T1 rating allows equipment surfaces to reach up to a blazing 450 degrees Celsius, which is only safe for gases that ignite at temperatures higher than 450 degrees. T2 caps that surface at 300 degrees. T3 is 200 degrees, T4 drops to 135, T5 is 100, and finally, T6, which is the strictest rating, caps the equipment surface at just 85 degrees Celsius for gases that ignite at anything above that. Now pay attention to the counterintuitive rule of opposites here. A higher T-class number actually dictates a lower, much stricter allowed surface temperature. Basically, if a gas is super sensitive and ignites easily from heat, you need a high T-class number, like T6, to guarantee a cool machine. But here is where even highly experienced engineers can fall into a massive trap: the ambient temperature trap. According to the exact standard, if an equipment nameplate doesn't explicitly mark an ambient temperature range, the default assumption is that it's strictly rated from -20 degrees to +40 degrees Celsius. So why does this matter? Well, imagine you install a T4 piece of equipment out on a deck exposed to the blistering tropical sun, or maybe in a stuffy equipment room where the ambient temp hits 50 degrees Celsius. Because your starting baseline temperature is higher than that standard 40 degrees, that machine is going to run hotter than it was tested for. Instantly, your T-class nameplate rating is completely invalidated. Your equipment is no longer compliant and definitely no longer safe. You literally have to re-verify it. And this brilliantly illustrates exactly why we have to match the equipment to the gas. Think of T-classes like oven settings for completely different recipes. Imagine a T1 gas as a really tough, hearty bread. It can easily sit in a hot 450-degree oven and be perfectly fine. But a T6 gas? That's like a highly delicate souffle that will completely collapse or, violently ignite if the oven goes even 1 degree past a cool 85 degrees Celsius. You would obviously never try to bake both at the same oven setting. In the exact same way, you can never, ever install hot T1-rated equipment in an environment where a highly sensitive T6 gas might be drifting around. Let's lock this concept in with a quick, rapid-fire check in the field. Picture this. You are out inspecting a facility. The equipment in front of you is rated T3, meaning its maximum surface temperature is capped at 200 degrees Celsius. However, you check your documentation, and the surrounding hazardous gas auto-ignites at only 180 degrees. So, compliant or not, take a second to apply that golden rule. If you said not compliant, you hit the nail right on the head. Because the equipment's maximum allowed surface temperature of 200 degrees exceeds the gas's ignition threshold of 180 degrees, you've got an extreme hazard on your hands. To safely operate in this specific environment, you absolutely must upgrade that equipment to a T4 rating or stricter. A T4 device is capped at 135 degrees Celsius, keeping you safely and comfortably below that 180-degree danger line. Let's move to and see how this builds into the bigger picture. Because what we've just covered locks into a broader physics toolkit that drives every single offshore safety decision.
First, we have the fire triangle: fuel, air, and an ignition source. Second, the explosive range: understanding the lower and upper explosive limits where the gas-to-air mix is actually capable of burning. Third, gas groups and vapor density: knowing how easily a spark ignites the gas and whether that vapor is going to sink to the floor or rise to the ceiling. And finally, the fourth pillar, the T-class system we explored today, which ensures the equipment itself doesn't become the heat source that completes that fire triangle.
So you now possess the complete foundational physics toolkit of explosive atmospheres. But as you can probably guess, knowing the physics is only half the battle. How do we take these invisible risks, the gas clouds, the heat limits, the explosive ranges, and actually draw them onto a blueprint? How do we color code a massive offshore platform so an electrician knows exactly what T-class equipment to install in room A versus room B? In our next explainer, we will decode the global zone classification systems, translating this invisible physics toolkit into the actual color-coded Zone 0, 1, and 2 maps used around the world. Until then, ask yourself, when was the absolute last time you checked the ambient temperature rating on your equipment? Think about it. Keep learning, stay focused, and I'll catch you in the next one.